So what is row echelon form for a matrix? Remember, we were aiming for this kind of form back with GEBS, remember? We have a square coefficient matrix in our examples. One's along the main diagonal, zeros all below. That's what we were aiming for in our GEBS problems. This would correspond to a square system with one unique solution. But what if that's impossible? What if we don't have one unique solution? Or what if we have a non-square system? You run into those things all the time in Math 254, linear algebra. In general, what is row echelon form? Well, this is an example of that, but what are some other forms? What are the general properties? So here are the properties of a matrix in row echelon form. Right. And then we'll take a look at this guy. All right. If there are any all zero rows, there don't have to be any, but if there are any all zero rows, then they must be sunk to the bottom of the matrix. Now, aside from such rows, every row must have a leading 1 as the leftmost non-zero entry. So you can have a bunch of zeros, and then the first non-zero entry has to be a 1, not a 2 or a 3. And these leading ones must flow down and to the right. They could be on a straight diagonal. They don't have to be. They don't have to be on a straight diagonal, but they generally have to go down and to the right. You could not have a leading one here and then a leading one over there. Okay? You can't have that. So take a look at this. Is this matrix in row echelon form? Well, there is a row of all zeros, and it's sunk to the bottom. Again, you don't have to have an all zero row, but if you have any, they must be sunk to the bottom. The leading non-zero entries are all 1s. This is a leading 1. Bunch of zeros, leading 1. Bunch of zeros, leading 1. So the leading non-zero entries are 1s, and they generally go down and to the right. Not necessarily on a straight diagonal, but they generally go down and to the right. Again, you never have a leading 1 like that and a leading 1 like that. You could have other ones. I mean, this one is fine, but it's not a leading 1. Often we do circle the leading ones in a matrix problem. They can help us in operations. Okay. So this isn't row echelon form. Now, there's a specialized form called reduced row echelon form, RRE form. And in particular, those are helpful in linear algebra in cases where you have infinitely many solutions. Also, it's a function of a matrix. If you give me a matrix of size m by n, whatever, and it's full of numbers, right? There's only one reduced row echelon form. Just like when we were talking about GEBS getting us this matrix over here, I said that you might get one row echelon form, your friend might have another row echelon form. Row echelon forms in general are typically not unique. I mean, if you have a matrix of all zeros, well, you have all zeros, that's it, right? But usually row echelon forms for a matrix are not unique. But every matrix with numbers in it only has one reduced row echelon form for a matrix. In that sense, it's a matrix function. In MATLAB, you have RRE, or programs might have RREF. So MATLAB is called Matrix Laboratory. It's a common program. And it has either RRE or RREF. Now, what are the properties of a matrix in reduced row echelon form? Well, it's got to be a row echelon form matrix. But on top of those properties, each leading one has zeros, not just below, which would be true for a row echelon form, unless the one was already on the bottom, right? But the leading one would also have all zeros on top, if anything. So each leading one has all zeros elsewhere in its column. Or in other words, each leading one is the only non-zero entry in its column. So let's take a look here. Well, let's take a look at this matrix. Erasing these. take a look at this matrix. How many of these entries would have to go to zeros in order to make this row echelon form matrix a reduced row echelon form matrix? How many entries and which ones would have to go to zeros? Look at the leading ones. This one is already on top of his column, and of course we have zeros down here. This one has zeros below, but in order to get reduced row echelon form, this 7 would have to go to a 0. This leading one, it's got a 0 below it, but we have to change these entries to zeros using elementary row operations. Don't just go in and make them zeros. You need EROs. Okay. And by the way, to get zeros here, you would eliminate up. You would use lower rows to help eliminate entries in higher rows. So for example, you could use the 1 in row 3 to hit the 9 in row 2. And then these zeros don't change anything up here, from here to here. And this one could also be used to hit this 4. This one would be used to hit this 7. And then if you go right to left in terms of fixing the columns, there are no leading ones over here, then you can change these to zeros, and then it becomes easier to change that 7 guy. Okay. Now, in Gauss-Jordan elimination, and you don't have to know this, but this is an alternative to GEBS. It's kind of a GEBS with additional pieces to it. Gauss-Jordan elimination is a matrix-heavy alternative to Gaussian elimination, in which we use elementary row operations to go all the way to RRE form. So if you love matrices and you hate letters like X, Y, and Z, you might prefer Gauss-Jordan elimination, and some students do use it. On a final exam, I would typically say on a matrix solve a system problem, you can solve the system using GEBS or Gauss-Jordan elimination, which again can be thought of as GEBS with some more pieces to it, or even a form of GEBS, where you actually eliminate up sometimes. Gauss-Jordan elimination. All right. Again, I mentioned before, MATLAB is a popular program that uses, it's RREF. It's RREF, a command that gives you the RRE form for a matrix of numbers. Okay, so here's the idea. Again, you will not be required to use Gauss-Jordan on the final. You can use GEBS in general. If you know GEBS in general, you won't be required to know the particulars of Gauss-Jordan on top of it. But, okay, here's the idea. Let's say that you have a system and it leads to this augmented matrix. Okay? Now, if you're going to use Gaussian elimination, then we're in row echelon form, right? This isn't row echelon form. You can then write the system in, say, X, Y, and Z, back substitute, and so forth. But if you want to use Gauss-Jordan elimination, then you also have to eliminate up. Use this 1, eliminate 3, eliminate this 3 also. Use this 1, eliminate the -2. And if you do that, you end up with, I show the operations here, you end up with this over here, which, by the way, is the unique reduced row echelon form for this thing up here. And also the guys below him. Okay, now what's one key benefit of Gauss-Jordan elimination? Because you might be going, wow, I did all that work with matrices. What's my reward? What's my reward for that? Look at this. What's your system? Write the system for this. Hey, x equals 1, y equals -1, z equals 2. It's right there. Basically, you can read off entries on the right-hand side, and you can ignore this row of all zeros down below. Although we tend to keep it in the actual matrix. We usually don't knock out an all-zero row just because we feel like it, but here we can ignore this when we're stating the solution. Again, well, right here, x equals 1, y equals -1, z equals 2. That gives us an order triple, x, y, z, 1, negative 1, 2, an order triple in braces. So you see, it is true that you have to do more work with the matrices, but hey, once you get all the way to reduced Row-Echelon form, you can essentially read off the coordinates of the solution off the right side, with maybe some modifications, like ignoring this 0 row. I won't talk so much about part I. So here's an example where you end up with a solution set with infinitely many solutions. You might see this kind of thing in Math 254, linear algebra. And if it does have any solutions, it'll be of this form, x, y, z, w. And it turns out that, again, for this system, it helps to put it in RRE form, meaning use Gauss-Jordan elimination. So then we go all the way down to Gauss, to this RRE form. You write down the corresponding system. You parameterize the free variables, which do not correspond to the leading one columns. You parameterize the y, meaning that you do something like you let y equals a, w equals b. All right. Solve for x and z, et cetera, and you get a solution set of this form. Again, you won't see a problem like this on our final, but essentially what you end up with is, get this, this represents a hyperplane, a two-dimensional hyperplane in 4 space. That sounds like a Star Trek thing, but if you're interested in that idea, a solution set that's a two-dimensional hyperplane in 4 space, go read this part. A and B vary over the reals, and that gives you a two-dimensional solution set. Okay. Next time in 8.2, we'll talk about matrix operations in general. You don't have to talk about solutions, or sorry, you don't have to talk about systems all the time. We see matrices elsewhere.